Well, today I would be talking to you on GC, Principles, Instrumentation and Application. It's a huge topic. I have to cover it in about 1 hour's time. So let us see how I go ahead with this kind of a challenge which I have. So chromatography is a tool which does a beautiful separation of the components. Okay, so that is what we are trying to learn. There are a number of diverse methods of separations, and then they can be used for separating mixtures. Some of them I have summarized in this slide. So you can see there are lots of methods apart from chromatography, but chromatography is one of the best techniques out of all of them. And that is why it got that kind of a popularity and being used worldwide for separation of very complex mixtures. Okay, so let us try to concentrate on chromatography as that's the topic of the day. Dr. Rama definitely told about Mikhail Sweat, who developed this technique, and he mentioned about how the name of chromatography has come. So I'm not going to talk much about them. Let us go and see what are the milestones of chromatography. So in 1903 he started. 1931 Lederer and Kuhn they started with, they reopened the kind of work which Mikhail Sweat did, because there was a big gap between 1903 and 1931. So they worked on LC of carotenoids. Then 38 TLC and ion exchange came into existence. 50 reverse phase liquid chromatography came into existence. James and Martin in 1952 was developed a gas chromatograph. Martin and Singe received a Nobel Prize in 1954. 1959 gel permeation chromatography came into existence, to which we call as size exclusion chromatography now. And 1965, the first HPLC instrument was developed by Waters, and it came as a commercial system. Well, so chromatography is such an important topic. During that development period, 1937 to 1972, 12 Nobel Prizes were awarded only on the subject of chromatography. So you can imagine the Nobel Prizes in chemistry were awarded to a topic like chromatography, and there were 12 Nobel Prizes were awarded. So the importance of chromatography was realized, and people got the Nobel Prize because whatever development they did, that was so useful to mankind. So the Nobel Prizes were awarded like that. Well, this is the kind of experiment with which Mikhail Sweat did, and you know already that he has separated plant pigments, and those were beta chlorophyll, alpha chlorophyll, xanthophyll, viola xanthine, and carotene. Now these compounds were separated in this order. Carotene came first, beta chlorophyll was the last to come out, and this is how the separation happened. The stationary phase was chalk powder, calcium carbonate powder, and he used the mobile phase, which is petroleum ether, and he washed the column with that, and at the end of the column he started collecting fraction of each one of those components, and that is how the separation happened. Now the question comes, why these compounds got separated like that? Why carotene came first and beta chlorophyll came last? What could be the reason for that? One reason could be the carotene was moving faster along with the mobile phase, so probably its speed was higher. It has a higher migration velocity, that is why it moved, and the least velocity was of beta chlorophyll, so it remained behind, and that is how the separation occurred. But then second question comes, okay, they have different migration velocities, that's fine. But why they had different migration velocities on this particular column? So we have to understand that the chalk powder or calcium carbonate is an adsorbent. So it was playing definitely a role, and that is why the separation happened. So the property of chalk powder was very important, and the kind of adsorption which was happening on the surface of chalk powder being a different, we got the separation, or Mikhail Sweat got the separation in that order. So in this column, he separated these 5 components on the basis of the adsorption phenomena of these components on the column material when the column was washed with the mobile phase of a petroleum ether. So in fact, he worked on one part of chromatography which can be considered as the liquid adsorption chromatography, and that is what it is called as, okay, so liquid solid adsorption chromatography. So this is the branch of chromatography, and he started working with this particular branch of chromatography. So we can define then the chromatography as a physical method of separation in which the mixture of analytes is separated using two phases. One is a stationary phase, like this chalk powder, and the other is a mobile phase, like petroleum ether, which percolates through the stationary phase. The separation occurs because of difference in affinity between the analyte and the stationary phase. And here the affinity is the adsorption. So what is important to have a separation? Of course, this kind of affinity of the substance with the stationary phase. Now, affinity is something which needs to be understood. Let us consider there is a marriage in a family, and then what happens? People start coming to the family of where the marriage is taking place. Those who are very close and good affinity with the family, they come few days in advance, they stay with the family, leave the place after a couple of days after the marriage gets over. So they stay for longer time with that family. Those who have little less affinity, they might be coming on the day before or the morning of the day, and maybe whole day they will spend with the family and then go. Those who have least affinity will only come for lunch. Okay, so that is what is the affinity is. So if the affinity of the compound is more with the stationary phase, it will stay longer. If the affinity is less, it will stay for a very less time, and it will get eluted very fast. So there are different aspects of then chromatography. One, as it was started by Mikhail Sweat, was liquid solid adsorption chromatography, called as LSC. Now the chromatography classification can be done in two ways. One is on the basis of mobile phase, and the first mobile phase which was written here is a gas as a mobile phase. And similar to liquid solid adsorption chromatography, there could be gas solid adsorption chromatography. There could be gas liquid chromatography. So when liquid is coated on inert solid, then the liquid acts as a media for having a partition of the sample between the two phases. One is the mobile phase, other is the stationary phase, which itself is a liquid, and that is how we get a separation. So it is called as gas liquid partition chromatography. Similarly, we have liquid solid adsorption chromatography, we have liquid liquid partition chromatography. Then we can have porous polymer, and the pores of the polymer will behave in such a way that they will take anything which is smaller than the pore. Anything bigger than the pore will not get into the pore, and it will get excluded from the pore. So that is why it is called a size exclusion chromatography, and this is used for polymers. So if the polymer is of the size which can enter into the pore, it will stay there. If the size of the polymer is bigger than that size of the pore, it will get excluded. So this is called as exclusion chromatography. Then we can use ion exchange resin, and that can be used for separation. So we can have two types of resins, cation exchange and anion exchange, and then we can separate the ions on the basis of whether the resin is cation exchange or anion exchange. We have separate lecture for that, so you will listen about this technique particularly very well. And then there is a thin layer chromatography, where we have a thin plate which is coated with silica or any other adsorbent, and you carry out a separation on the plate. You can carry out separation on paper also. Now these kind of chromatography, they are also called as planar chromatography, because the plane of the surface is used for separation. So these are also part of liquid chromatography, because liquid mobile phase is used. There is one more branch which I have not listed here, which is called as supercritical fluid chromatography, where we can use supercritical fluid as a mobile phase, and then we can have a column which will be able to separate the components. So the supercritical fluid being a mobile phase, which has a property of a liquid as well as property of a gas. So it is somewhere in between the gas and liquid chromatography. It's by itself is a separate subject, so we are not going to talk much about that. Well, let us see how the separation happens on a column. Okay, so I'm going to show you something here. So you can see the components are going through the column. There is a mobile phase. Probably it is not seen. There are very small things over there, but they are not seen, which is a moving mobile phase. So this is how on the column you can get a separation, and you can get, now there were three different compounds they are given you, a separation like this. So this is how chromatography works. So you have a sample introduced at the one end of the column, the mobile phase is moving, and then the sample components, as they travel through the column, they get separated because they have different kind of affinity with the surface which is there, and that is how the separation can happen. Okay, so these are the kind of peaks which we get, as you have already seen the peaks which have come along with the, as the column is separating the components. Now I am getting these three types of chromatograms for the same sample, maybe under three different conditions. The two components are same. Now looking at it, without knowing much about chromatography even now, you can definitely say the last one, that is C, is a better chromatogram than the other two. The first one is the one where we are not getting good separation. Second one, we are getting some separation. And third one, we are getting a good separation with very sharp peaks. Now, this is what we need. We want to have a good separation in less time. As you can see here, these two peaks are getting separated, but the time taken by the time the second peak comes out is much higher. And if you compare these two peaks, the time taken is much smaller compared to this. And then they are well resolved, well separated. So the punchline for chromatography is that we should have a good separation in less time. And every chromatographer has to work in this direction. Whenever he gets any sample to be separated by chromatography, he should develop a method in such a way that he should get good separation in less time. So keep it in mind always that this is what is required. This is separation, but not in good time. This is poor separation, and time taken also is large. Okay, so obviously this is the best method of separation where you are getting good separation in less time. This is what happens when the sample is suppose introduced here. It starts getting separated. As it travels through the column, as it migrates through the column, the separation starts increasing. So you will see here, B is here, A is here, and finally A will come out because this is the migration of the sample as it moves. And as you can see, as the peak starts moving in the column, it starts becoming broader and broader. So here it was not broad, but as it travels through the column, the molecules which are moving in the mobile phase and onto the column, they start becoming more diffused and diffused and diffused. So the band width or the peak width starts increasing and the peak becomes broad. Now this broadening of the peak is very, very important in chromatography. As we have seen in the previous slide, that broadening of the peak takes more time for compounds to get eluted. Another thing is, within this time frame, from the first peak to the second peak end, probably if the peaks are of beautiful shape, I can have one more compound separated here. So the separation efficiency of the column could have been increased if the peaks would have been not broad as this. So the theory of chromatography is around broadening of the peak. And then there are two theories which are proposed to explain the band broadening. One is called as plate theory and other is called as rate theory. Within short time, I will try to explain these two terms or two theories to you and try to see whether you can understand something out of that. Let us imagine that a chromatographic column of L centimeter length is divided into n small section of equal lengths or height. Okay, so let us see what happens. Okay, so we have two columns. I am putting another column also. So let us look at the column on the left. Okay, where my highlighter is there. Okay, so here you can see these are the plates inside the column. Now if you calculate this column in the length L, there are a number of plates. Okay, so the distance between these two lines, this is a plate. Okay, and every plate has its own height. Okay, so this column has more number of plates, and if you see the other column which has less number of plates with the same length L. Okay, so L length is same, but in two columns the number of plates are different. Now as it is clearly said, this is a theoretical concept. There are no number of plates visible. You cannot say that this column has this plate, I can see these plates. No, you cannot see them because it is a theoretical concept. What is assumed that when you introduce your sample on the top, it gets distributed in the first plate, and then it moves to the second plate. And as it moves, depending upon if the sample has two components, depending upon the affinity of the two components with the stationary phase, one component will move faster, the other component will remain behind. And slowly as they move forward, they will get separated, but the separation at each stage would occur only on this plate. Plate by plate, they will go down and they will get separated. And then what, because of so many number of plates, we get a good separation and very sharp peaks. But if you look at here, if I put the sample over here, it will get distributed in this entire plate. Okay, so this is the plate height. Then it will move to the second plate. So here itself it has already got broadened. As it moves here, it will get further broadened. And then it will also have, because number of plates being same, it will not have enough time to get a separation as it comes out, and then both the components will not get separated. And you can see the peaks which was there in the first chromatogram in the previous diagram ABC. It will come like that. So when you get such a kind of a separation, you can say that the column has less number of theoretical plates. If you get a good separation and sharp peaks, you can say that column has more number of plates. So number of plates being more, we can say that column has a good efficiency. So efficiency of the column is denoted by term n, and n is number of plates in a column. Now, there is one more term which comes along with that. What is the height of each plate? Because you calculate number of plates like that. So 1, 2, 3, 4, you can calculate the plates, and then each plate has its own height. So height of the plate then can be easily calculated knowing the length of the plate, length of the column. H is equal to L by N. So length of the column divided by number of plates is height of the theoretical plate, okay, and which is termed as HETP, height equivalent to a theoretical plate, HETP. So if you look at these two terms, H and N, you can say that they are inversely proportional to each other. So if the column has to be good, it should have more number of plates or less value of H. HETP should be small. Okay, so this is what the plate theory talks about. So plate theory only looks at the static part. It looks at that there are number of plates and the diffusion of the sample happens on the plate, and as if the plate height is higher or number of plates are smaller, they will become more and more broader. Okay, so this is what in short a plate theory talks about. We have to calculate the number of plates. So there is simple equation by which we can calculate number of plates. If we know the retention time of the peak, that means the time at which we have injected sample into our chromatography equipment until you get the peak maxima, that is called as retention time of the peak. So if we have a retention time of the peak, and if we calculate the width of the peak in terms of time, not in terms of centimeters or millimeters. So the starting time to the end time, if we know, then the difference between the end time and the starting time will be the peak width time, and we know the time of the peak when it comes and gets eluted, and the peak maxima is retention time. Then we can calculate number of plates by simple formula 16 into TR upon W bracket square. If the peak is not complete and you have another peak coming like that here, then many times we use another formula which is n equal to 5.54 into TR upon W half square. So what we measure? We measure the peak width at half the height of this peak. Okay, so which we can easily measure. If the peak is broad and it is going like this, then we really find it difficult to measure the width of the peak. So W sometimes become difficult to measure, and especially it is very difficult when you have another peak coming like that. So the first peak has never come to the base, then it is very difficult to find out the width of the peak. So we use another formula, and this, by using this formula, we can calculate number of plates. Now we come to another part of the theory, which is called as rate theory. And in rate theory, we consider, because chromatography is a dynamic process, it is not a static process. Everything is moving, your mobile phase is moving, your sample is moving, only stationary is the column. But then that also plays a different role, because in the column we have particles which are coated with liquid, or if it is adsorbent, which you have particles which are adsorbents. And then what happens? Their size of the particle becomes important. Okay, so the diameter of the packing particle becomes important. Then thickness of liquid coated on stationary phase becomes important. Diffusion coefficient in stationary phase, diffusion coefficient in mobile phase, linear velocity of the mobile phase, all such factors become important because it is a dynamic process. Then they calculated there are 4 variables which can talk about the kind of separation which can occur onto the column, and which are responsible for separation, and which can be responsible for giving us low value of H. We want to have H to be lower, N should be higher. So H has to be lower. So this equation, which is developed by Van Dimter, this equation has these terms A, B, CS and CM, and these terms are described here. These are called as the multiple flow path, the longitudinal diffusion, which is given by B, and then there are mass transfer to and from liquid stationary phase or stationary phase, and mass transfer in the mobile phase, which is denoted by CM. This is denoted by CS. This is B and this is A. So these factors are important, and if these factors are to be less, then only you have value H to be less, and then that will say that number of plates are higher, or H is better, or H is lower. That means column efficiency is good. Height of the theoretical plate has to be small, and all these factors will add to that. So we have to understand some of these terms if we want to really find out how we can get H value lower. As far as GC is concerned, the molecular diffusion will be always higher, because gas can diffuse very fast compared to that of a liquid. So in liquid chromatography, B value is very less, while in case of a gas chromatography, B value is higher because gas can diffuse much faster. In case of a gas chromatography, CM is lower because mobile phase mass transfer is less, because the mobile phase being carrier gas, it doesn't take part in separation. It has the purpose of only carrying the sample forward. So this factor is less, only CS remains. And then we have equation which will be A plus B upon mu plus CS into mu. Now A is something which is called as multiple flow path, and that has to be defined in properly, and that is what is important factor also, because every column which is packed with the particle size and the variation in the particles and the way it is packed, the sample would start passing through the gaps between the particles, and what will happen? Some particles will find an easy path to go to the other side, while some sample molecules will find a longer path to go to the other side. And irrespective of whether the sample is getting retained on the column or not, whether it is going to get adsorbed or whether it is going to get partitioned on the column or not, there will be some diffusion taking place just because of how the column is packed, and that is called as AD's diffusion, which will be always there in a packed column. So when you use a packed column, AD's diffusion will be there. And if I use a capillary column, when we go to the column part of my presentation, the capillary column is an open tubular column. That means the tube is open, there are no particles inside. The stationary phase is on the wall of the column, and the column is totally empty inside. So there will not be any kind of AD's diffusion there. So there is no multiple flow paths possible. So A becomes 0, and then that will make H become smaller. And when we use a capillary column, H becomes very small, and that is why the column efficiency of the column would be higher. Number of plates will be higher, as H is inversely proportional to number of plates. So you will have a better separation when you have a capillary column. So this is how the theory talks about and tells you why capillary columns are preferred. Now go to other part. It will take time to talk about the mathematical part, and then I will not be able to complete the rest of the things which I want to talk about, the instrumentation and application. So I will cut it short here. Anybody has any questions, I will be able to sort. Now here mu is the linear velocity. I need to talk a little bit about that. And then, as in one place it is in denominator, other place it is in numerator, what happens is the equation which is there, where if it is HETP is plotted again linear velocity, it will have a equation which will give a parabolic curve. And then at one minimum value of flow rate, linear flow rate, the value of H will be linear. H will be small. So generally when we do any experiment, we try to find out what is the linear velocity at which H is small. And that will tell us that this is a better velocity, linear velocity at which H is small. And we try to use that as a linear velocity. And we generally prefer slightly higher, because when we use a higher flow rate without much of a compromise onto the value of H, because you can see H is almost similar even here. So I can use this value of linear flow rate, no compromise on H value, but increasing flow rate, I will not compromise on separation, but I will get a faster separation because flow rate is fast. So the components will get eluted fast. So I will be able to use this this curve, which is called as Van Dimter's plot, for calculating the linear velocity and using that for the purpose of the chromatographic run which I want to work with. Okay. Well, we are coming to some more mathematical terms which are very critical in chromatography, out of which one is called as capacity factor. You have to understand this term very well, because when we put a sample onto a column, it gets carried away by the flow of a mobile phase and it comes out. The mobile phase itself starts from the same point and comes out. So this is the time at which, if we have introduced sample here, mobile phase comes early because it has no retention on the column. It will move very smoothly and you will get a peak because of mobile phase itself, which is called as Tm. Then you will get a peak for your sample. So what it shows, that you are getting a peak much after the peak of your mobile phase. That shows that the column has a capacity to hold your sample, and that has to be there. If your sample comes here itself at this point, that means column is not able to hold your sample, and such a column is useless because the sample has to have a capacity on the column. So the capacity factor is very important, and it can be very easily calculated by the equation K dash is equal to capacity factor. If you know the TR of the retention time of the peak of whatever is coming out, you know the retention time of the mobile phase, TR minus TM upon TM will be your capacity factor K dash. Now, if you look at this, if I have two components, what is expected? The second component should have a capacity factor somewhat different. It can be here or it can be here. It cannot be same. If two components have same capacity factor, what would happen? They will both elute at the same time. They will not get separated. So we need to have some more factor, and which is called as a selectivity factor. So each is a ratio of two capacity factors. That means these two components have two different capacity factors. One comes little later, one comes little earlier. So they get separated. So what we are talking here about, that when you have multiple components, the column should have a selectivity for each component, so that the capacity factors being different, they will be getting separated. So the column also should have selectivity factor, and selectivity factor is nothing but the K2 dash upon K1 dash, if these are two peaks. If there is another peak here which is separated, we can calculate its capacity factor. It would be K3 dash, and the capacity factor ratio between these two peaks could be K3 dash upon K2 dash. So we can calculate the alpha value for the number of peaks which we have. And the capacity factor and selectivity factor both are important. Column should have a capacity factor. Column should have a selectivity factor when it has multiple peaks. Each peak should get retained on the column. The column should be having selectivity to hold that compound for more time than the other peaks, so that they get separated. So these two factors are very, very important in chromatography. There is one more factor which talks about resolution. And resolution is very critical because we need to have a separation. And separation, we don't want separation like this. We don't want separation like this. We want separation where there is a baseline resolution. So the two peaks have come to the baseline. And when we get this kind of a separation, we say these two peaks are well resolved. And there is a factor which is called as resolution factor, which is calculated on the basis of this. This is the 2 times TR2 minus TR1 upon WA plus WB. Actually, what is done is the difference between the two times divided by width of the peak A plus width of the peak B at half its height. So WA by 2, WB by 2, and that is how this 2 goes up. So we say that 2 into TR2 minus TR1 or TRB minus TRA upon WA plus WB. Okay, so that is how you can also measure the resolution factor, and resolution factor has to be more than 1.5 to get this kind of a separation. Here it is just close to 1, here it is 0.75. So this is not well separated, this is not good separation, but this is a good separation where resolution factor is 1.5. So all these factors are very important. Okay, so we need to understand a little bit about that. This is the chromatogram which I have shown you, 3 peaks. All the 3 chromatograms are same, and everywhere I am trying to give you some information about the chromatogram. Here I am talking about width of the peak, which is important. Now as you see, from peak A, which is come first, B has come later, C has come next, there is a peak width increase. So the compound gets more diffuse as it spends more time on the column. So WA and WB and WC, they have different widths. This has to be remembered. So as the compound gets eluted much further, the width will start increasing. Here we are talking about time. So we are talking about retention time of the peak A, retention time of the peak B, retention time of the peak C, and they are well separated. And under given condition of the chromatography, you get A eluted exactly at the same time, B will get eluted exactly at the same time, and same thing about C. So you will be able to use this for qualitative analysis. So under given condition, if you have a sample and the sample, one of the sample components gets eluted at this time, you probably may say that this compound may be present in my sample because the retention time of both of them being same. So this is the one which is used for what we call as a qualitative analysis. There is one more factor which we just talked about, resolution. So here we talk about the resolution between 2 consecutive peaks. Resolution is always talked about 2 consecutive peaks. So this is the resolution between A and B. This is the resolution between B and C, and all these should be more than 1. So this resolution factor also should be more than 1.5. This resolution factor also should be more than 1.5. So whatever number of peaks you have in your chromatogram, all of them should get resolved with a resolution factor of 1.5 between the adjacent peaks. Of course, this and this will definitely get resolved with much more than 1.5. But what is more important to us is that 2 adjacent peaks should get well resolved. Okay, so this resolution is very important. And then this is third thing where I'm talking about area under the curve. So the area of A, area of B, and area of C. Now the area under the curve is responsible for the concentration. So if I have a particular concentration of A, the area of the peak would be some amount, which can be given by the instrument in terms of some counts. So area under the curve A, when I have a standard, I will measure the area of the curve for A as a standard, and then compare it with the area of the curve under the curve which we get for unknown A, unknown concentration of A, and then we can find out the concentration of A, concentration of B, concentration of C, provided we have individual standards available with us. Okay, so this gives us quantitative information. This is about a GC which we have already seen, and I will not, this is a cartoonist view of a GC, carrier gas, injection port, then the column, and the column oven, because sample has to be heated in the injection port, get vaporized, and vapor should not get condensed anywhere. So the column is heated, and then it goes to the detector, and from the detector you get a signal, and that is plotted. Now these kind of distances are not there. If you see the instrument, the carrier gas can come from the back, it comes to the injection port. You put the sample through the injection syringe into the port, and there is a heater inside which will heat the sample component, they will get vaporized, then it will go through the column, and from the column it comes to the detector. Detector is just sitting here and detector block also is heated, so that there is no condensation of any vapors right from the injection port all the way to the detector, and everything will be in a vapor form, and whatever signal comes out from the detector, it is analyzed. So there is a data system which will give us the chromatogram there. These are the components of a GC, carrier gas. We have helium, argon, nitrogen, hydrogen. These are the normal gases which are used. Helium nowadays we are trying to avoid, and we work with nitrogen or hydrogen depending upon the detector of choice. So these two gases are preferred. Helium is the gas which is very costly, and it is the scarcity of helium is coming up, and because of that helium needs to be avoided. Sample injection system, so we require to have different injection ports. We'll talk about that. We require chromatographic column. There are a number of columns which are available, pack column as well as capillary columns. We require oven, as we have already said. We require oven to have temperature increase, so you can have an isothermal condition, temperature will remain constant, or you can program the temperature of the oven as it will go from low temperature to high temperature. Detector, we can have FID, TCD, ECD, and many other detectors are available. There are choice of detectors depending upon the sample, and then we have a data system readout which will give us the chromatogram, which will give us about the concentration of various components in the peak. Everything is possible to be measured. Okay, so carrier gas, generally we have, as we said, hydrogen, nitrogen, helium, argon are the common carrier gases. The flow rates are 25 to 150 ml for pack column and 1 to 25 ml for capillary column. Generally it is much less than higher side. 25 to 80 or 1 to 10 ml per minute are nominal flow rates which are used in packed and capillary column respectively. We go to the injection port from the carrier gas. Injection port is generally, which is preferred, is splitless injector. So here it is a splitless injector. Carrier gas comes from here, and this is metal surface which is heated. So the injection port has to be heated so that the sample in a liquid form gets evaporated and the vapors of the sample goes to the column. Now there are two ways. One way is to have a split. When the sample concentration is higher, we have to split the sample so that the part of the sample will go out, and then only part of the sample will go onto the column. By that, we are not going to saturate the column, especially in case of capillary column, which is put inside the injection port. It has got a stationary phase coated on the wall of the column. The stationary phase quantity is very less. So if the concentration of the sample is high, it will get coated with the sample, and it will get the saturation, and the resolution will get affected. So the capillary column will not work effectively if you put a large sample here. So we put a split ratio. Because of the split ratio, more amount of sample will go out and very small amount of sample will enter in, and you will get very good separation of the sample happening because of the capillary column, which gives you higher efficiency. Now there is one way. If the sample concentration initially itself is very low, then you can have a splitless injection so that the entire sample will go onto the column. So the injection port can be operated in split mode or splitless mode. Splitless mode is used when sample concentration is low. Split mode is used when sample concentration is high. If you have a gas injection, that means you are trying to find out the purity of the gases, you can have a loop, and the loop can be filled externally by the cylinder pressure, and at that time the gas is directly flowing into the system. When we change the position of the valve, then the carrier gas will start flowing like this. It will flush the sample from the loop, and then it will get into the gas chromatography, where the column will separate them and will tell us about the impurities in the gas. Okay, so this is a mechanical injection device with a valve which can be used for gaseous injection. There are other injection like PTV, where we have a sample containing different components with a low boiler as well as high boiler. So we have to have a temperature programming in the injection port itself. So initially we take the sample inside and then allow it to be there onto the surface of the packing material, and then heat the material at a low temperature. So the low boilers will go onto the column. After low boilers are analyzed, high boilers need to be taken out. So we increase the temperature of the injection port so that high boilers will now come, high boiling point materials will come, and then they will get onto the column. And that is how we can have a programmed temperature vaporization for the sample components where we have a different boiling range of the sample. There are low boiling compounds, there are also high boiling compounds together. Well, we go to the oven. We have isothermal and temperature programming. We'll see the advantage of when we have isothermal, it is taking a very long time. The separation is good, but the column is eluting it with very slow flow rate, slow rate. So we have good separation in long time, which we don't want. Here we have used the temperature much higher, so the these compounds are not getting separated at all. Those elute early, they are merging together, so we are getting uh, poor separation in less time. So we don't want that. What we want is a temperature programming here. Because of the temperature programming, all the components are getting well separated. This is what we want. So this is this is a good separation in less time. That is what we intend. Okay, so there are different columns now, pack columns, which are made up of stainless steel or copper, and they are having a length of about 1 meter to 4 meter in length. So they are short columns. While we have a capillary column, so there are a lot of packing materials which can be used, and generally the packing material which is used is characterized by the kind of polarity. So we have the non-polar columns, we have the semi-polar columns, we have the more polar columns. So we have a lot of stationary phases depending upon the nature of polarity of the stationary phases. Now we have capillary columns which have got a very high length and small diameters. So diameters of the capillary could be 0.1 millimeter to 0.53 millimeter. So one which is having 0.1 millimeter is called as microbore column. The one which has got 0.53 millimeter diameter is called as macrobore column. Now there are again three types within that, where one is where the liquid stationary phase is coated on the inner wall. This is called as wall coated open tubular column. There is another one where we have an inert support coated inside the inner part of the capillary, and on this surface a liquid is coated. So it is called as support coated open tubular column, called as Scott column. And then there is another column where we have a porous polymers which are coated inside, which act like an adsorbent, and this column is called as porous layer open tubular column, called as plot column. This is a gas adsorption chromatography takes place here, and here it is a gas liquid chromatography, liquid coated on inert solid or liquid coated on wall of the capillary. So this is called as a gas liquid chromatography. Again, this is how the capillary columns are prepared. They are fused silica is drawn and passed through the drawing motor, and when it is heated, so it melts slightly, so you can give a particular shape to it, and the final product comes as a capillary column. Okay, so capillary columns need to be made outside. These are the nature of the columns. Again, everything depends on the polarity. So these are non-polar, intermediate or non-polar columns. We have intermediate polar columns, we have strongly polar columns, and we have very strongly polar columns. So depending upon the nature of the liquid which is used for coating, the surface becomes non-polar to polar. Okay, so here you can see we have a diphenyl group attached to it, and here it is dimethyl groups attached to it. So dimethyl or diphenyl group compounds are generally come under non-polar or intermediate polar category. So these are intermediate polar, these are non-polars. When we have a cyano group here, it becomes a semi-polar. When we have only one phenyl group here, it is little semi-polar. When we have cyano group attached here, it becomes more polar, and here also we substitute phenyl group or cyano group, it becomes more and more polar, like it is done here. Here there are both the times. Here instead of phenyl group there are cyano groups. Here there is one cyano group and one phenyl group, so this becomes very strongly polar column. So as we do the substitution onto the silica here, we get different kind of a polarity on the column. Then depending upon the polarity of this sample, we choose a column. So these are the sample components which are categorized into non-polar, weak intermediate polar, strong intermediate polar, and strongly polar compounds. And depending upon the nature of these sample, we choose a nature of column. And as we always know, like dissolves like. So for polar samples, we use a polar column. For non-polar samples, we use a non-polar column. I'm not going into that. We'll see the detectors now. There are several detectors which are used, and main detectors are flame ionization, thermal conductivity, electron capture, flame photometric detector, nitrogen phosphorus selective detector, and mass spectrometer, which will be dealt by Dr. Ramakrishnan during his talk. Uh, then we go with the most common detector, flame ionization detector, and here we use hydrogen oxygen as the gas for producing the flame. Nitrogen can be used as a carrier gas, and when we form a flame here at the tip of the flame, the sample comes from the column, say capillary column, burns here, and as the sample component has hydrocarbons or carbon and hydrogen, all those compounds will produce ions in the flame when they burn, and these ions will produce the ionic current, or they get deposited here. More ion current will be formed between this, and that current is amplified. You have initial voltage which is applied here, which will set a very minimum ionic current, but when organic compound burns here, the current will be higher and you will get output. So that is how the FID works. So it is useful for all organic compounds, and that is why it is most commonly used, because most of the time we work with organic compounds, and FID becomes that way a very general detector. It is not a universal detector because it cannot be used for non-organic compounds. Even if the compound has carbon, it cannot be used for just CO2 or carbon monoxide. It should have both carbon and hydrogen. That is what is very essential. It cannot work with inorganic gases. It cannot work with water, though water has hydrogen, but it doesn't have carbon, so it will not work with water. So it is a good detector for pollution monitoring, air pollution or water pollution, because by itself it doesn't give any signal for those compounds. So this is what I have already explained. We go to thermal conductivity detector. Here we use 4 filaments of either platinum or any other noble metal, and these filaments, when they have very small diameter, they act as a resistor. So these are acting like a resistor. It is just a thin wire which is used, and these are 4 detectors here. 2 detectors see carrier gas only flowing through them. Carrier gas comes out, goes through the injection port, goes through the column, and then comes here to the sample side of the detector. When initially, when only the carrier gas is flowing through the system, all the 4 detectors will have same uh, voltages, same resistances, and because of that, the output at the uh, Wheatstone bridge circuit will be 0. But when a sample comes into sample compartment of the detector, sample will be mixed with the carrier gas. The thermal conductivity of the mixture will be different than only the carrier gas. So because of that, either less heat or more heat will be carried out by the sample, and there is one property of this filament, that they have a positive temperature coefficient of resistance. That means if the temperature increases, the resistance will increase, and that way if the less heat or more heat is carried by the filament temperature will either increase or decrease, and depending upon that, the resistance will change, and this resistance change will affect the balance of this Wheatstone bridge. It will become imbalanced, and because of that, there will be output which is indicated as a signal, and you will get a peak as the peak starts coming out from the column. These are the thermal conductivities of the various gases. We prefer hydrogen as a carrier gas because it has the highest thermal conductivity with respect to all other gases. So it can give you a little higher sensitivity compared to other gases if they are used. Okay. Then we have electron capture detector, which is used for determining the halogen containing organic compounds. We use nickel 63 as a radioactive element which emits beta rays. So the beta rays are in this area. The nitrogen flow which we are using as a carrier gas, when it comes here, beta rays has a property that they can ionize the gases. So the nitrogen gas will get ionized and it will produce a higher current which will flow through this detector, these electrodes, and you will get higher current which is produced because of the ionization of nitrogen. Now, if sample comes and if the sample has the electron affinity, that means it has got a halogen containing organic compounds. When it comes in this area, it will capture the electrons given by nickel 63, the beta rays which are coming out. And because of that, the current produced at this electrode will drop because electrons are captured by these compounds, and the drop in current is measured as a signal here. And this detector is very sensitive to halogen containing organic compound, and it is a very good detector for halogen containing pesticide monitoring in food. So these are all the pesticides which are monitored by ECD, and they are all halogen containing compounds like DDT and DDE and all other anachlor and so many other compounds which can be measured by using a capillary column here. Then we have a flame photometric detector, which is where when we use a flame, nitrogen and phosphorus containing organic compounds, when they burn in a flame, they give you emission lines. And these emission lines can be measured by a photomultiplier tube. So we have a film which will only allow the radiation which comes from the sulfur, which has a wavelength of 394. So if I use a filter of sulfur for 394, 394 nanometer radiation will go to the detector photomultiplier tube, and it will detect the sulfur containing your organic compound. For phosphorus, 526 nanometer filter is used, and then it will be able to measure phosphorus containing organic compounds. So by using this detector, one can monitor the phosphorus and sulfur containing organic compounds, and it gives us a very high sensitivity for these compounds. There is another detector. This is the gas chromatogram for sulfur containing thiophenes and other compounds which are analyzed by the FPD, flame photometric detector, which is sensitive for sulfur and phosphorus. There is another detector which is called as nitrogen phosphorus detector. So it is sensitive to nitrogen and phosphorus containing organic compounds. There is a rubidium silicate bead which is kept above the flame here, and this bead is having a rubidium. Rubidium is an alkali metal element, so because of the heat here it gets excited, and when it gets excited it transfers the energy to nitrogen and phosphorus containing organic compound. They get ionized more than the hydrocarbons, and the detector will detect them much better compared to if you have a just flame detector, flame ionization detector. But just because of this bead, it becomes sensitive for phosphorus and nitrogen, and it gives you signal 10 raised to 4 times than the hydrocarbons. So it can easily identify nitrogen phosphorus containing organic compounds. And again, it is related to pesticides because there are a lot of pesticides which contain nitrogen and phosphorus. And this is the example of herbicides being analyzed by nitrogen phosphorus detector. And all these herbicides are separated on capillary column, and they can be analyzed at very low level by using nitrogen phosphorus detector. Well, this is the comparison of all the detectors. Your FID has a very long linear dynamic range. It can come to nanogram level of detection. When you consider ECD, it goes less than picogram. NPD can go closer to picogram level. NPD here also in phosphorus mode is better. FPD can go here, and when you look at MS, it is the most sensitive detector. It is even more sensitive than any of these ECDs, and that is what is going to be considered by Dr. Ramakrishnan. And as you can see, MS is a universal detector as far as GC is concerned, GCMS is concerned. It can detect gases as well as it can detect all these compounds, whether they are halogen containing compound or nitrogen containing compound. There is no specificity. It is a universal detector, like a thermal conductivity detector. I will quickly go through GC applications. So there are a lot of GC applications. Food and flavors is one of the main areas because all the flavoring compounds are volatile in nature. So it is very good to analyze flavors by using GC. So alcohol beverages can be analyzed by GC. All are volatiles. Then we have essential oils in tobacco. Essential oils are there in many plants, like we have peppermint oil, we have spearmint oil, we can have a eucalyptic oil, you have a clove oil. So all eucalyptus oil, so all these compounds can be analyzed because they are volatile in nature. They can be analyzed very well by GC, and all the compounds are analyzed by FID as a detector. Okay, so if you look at the detector which is used is FID. So FID is a good detector for all general purpose compounds. We don't use uh, unless and until it is desirable to use a high sensitivity detector. We don't go for electron capture or any other detector unless that kind of a sensitivity is required. Otherwise, FID can take care of even pesticide analysis. Unless and until we want to do pesticides in food at a very low level, we will not go to those detectors. If I just want to analyze pesticides as for the quality control of the particular pesticide, I do not need to use special detectors. Fatty acid methyl esters are used generally for all the oils like soybean oil or any other oil. So that's a good detector. And then generally what we do is we prepare derivatization of these fatty acids, convert them into methyl esters, because long chain fatty acids will give a very long tailing peaks, or some of them will come after very long time on normal columns. So once we convert them into methyl esters, they become volatile, they become non-polar. So this is one way of working in a GC, that you can derivatize the compound, convert it into other form, which is making it non-polar, and then you can analyze these fatty acids by converting them into methyl esters. So you have fume, that is fame of sunflower oil, fame is fatty acid methyl esters. We can have fame of soybean oil. We can have so many other compounds which can be analyzed, steroids, blood alcohols, then rapeseed oil, and chlorinated aromatic compounds. Now this derivatization is also useful when we analyze the inborn error of metabolites. That is, there are metabolites which are newborn babies will have those metabolic disorders, and they can be analyzed by converting them into their methyl esters. Okay, so they need to be analyzed that way. Pharmaceuticals is one of the area, but many pharmaceutical compounds are mostly analyzed by LC because they thermally degrade. But some of them, like alkaloids, uh, conjugated estrogens, then antihistamines, some of them are volatiles and they can be analyzed by GC. Okay. Gas solid chromatography is generally used for gaseous mixtures or low boiling your hydrocarbons, C1 to C4 hydrocarbons. They can be analyzed by using the gas adsorption chromatography. Okay, so you use molecular sieve is one of the column. Porous polymer can be used for separation of these inorganic gases. Okay, molecular sieve can separate even air, oxygen and nitrogen into individual compounds. So here you can see hydrogen is separated, carbon dioxide is separated on the same column, oxygen is there, nitrogen is there. All these compounds can be separated on molecular sieve column. So we'll come to advantages of GC. GC gives you a fast analysis compared to LC, because LC we use a pack column. Pack column take longer time for retention. Column capacity is higher, capacity factor is higher, so they take a longer time. So GC is much faster compared to the LC. It gives you high resolution because in a capillary column which has got a very high length, we can use capillary column up to 60-meter length or 100-meter length. Nominal capillary column is about 25-meter to 30-meter in length, and because of high length, it has got more number of theoretical plates, and because of that, it has high efficiency, and you can get a much better separation and much better sensitivity because of GC with capillary column. It has some disadvantages, definitely. It has disadvantage that anything above 380 degrees centigrade cannot, if the boiling point is more than that, generally it cannot be analyzed. There is some thumb rule that if the vapor pressure of the analyte at is 60 torr at the particular temperature, say 380 degrees, if the compound has a vapor pressure of 60 torr, then probably it can be analyzed by GC. Analyte should have a boiling point below 500 degrees centigrade and should have this pressure at 380 degrees of 60 torr, then probably even these kind of compounds can be analyzed by GC. Not suitable for thermally labile compounds, however, because thermally labile compounds will decompose before that temperature, and then we don't want to look at decomposed product, we want to look at the actual the component. Then for identification, we require spectroscopy, usually MS, for confirmation of the compound. So there is a limitation for GC that there are only 10% compounds which are volatile, 90% compounds are non-volatile or thermally labile. So we have to work with LC for them, and you have separate lectures on HPLC and ion chromatography. The part of lecture which I had to cover was on GC, and I think I have covered that part in a short time, and I hope I have given justice to that topic.